Okay, so this is a big pleasure for me to come here to Sevilla. This is our second time to Sevilla because the last time we came here for the PSCC conference, 20 years ago, about, yes. So, yeah, I wanted to talk about the evolution of control for the power grid, and we'll start pretty much from the beginning. But first, everybody's seen this picture, and you've seen the picture of the world, this is one sign of what mankind has done. This is something that is man-made, and you can see it from space. So when the power grid was started, the power grid sort of came together over time, and there were two reasons to interconnect all the power companies together. And one was the economics, because you could transfer power from cheap areas where you can produce it cheaply to wherever the load was, the load centers were. And the other reason to interconnect was reliability, because if you couldn't supply the electricity right then you can get the backup from your neighbors. Okay, so that was the main reason why in the 1920s, 1930s, people started interconnecting all with large grids. So as soon as that happened, actually even before people started interconnecting, the idea of looking at the whole grid came up. So even if you had more than one generator, somebody will have to make sure which generator is producing how much power, right? So the idea of a control center started very early on. But this became more critical when you had several power companies connected together. So then each company had to make sure that the transfer of the power was according to your schedule, your what you wanted. So if you think of the old days before computers, there was no way to get this information into one control center except with hard wires. So everything you did was, if you had a measuring instrument in a power plant, if you had a measuring instrument in a substation, then that had to be connected with a hard wire where that instrument, the measurement, was brought into the control center. And the only way to see this measurement was on instruments that were put on the wall. So if you're a control room operator, all you had was several of these dials on the wall, which showed you voltage, power, VARs, all of these measurements. In addition, by the way, if you wanted a recording, if you wanted to know the history of what happened, then the only way to record this was with a pen, right? So you had the pens, you had the wall, and then the other thing you wanted the operator to be able to do is to change things in the thing. So the main thing you changed was breaker closing and opening, and that also had to be done by hard wire. So if you had a switch, if you moved the switch mechanically, then there's a hard wire which sent that signal to the actual breaker in the field, and it opened up. So the idea was, this was the hardwired. Now what happened was that around 1930, when different power companies connected, you had to make sure that the amount of power being transferred in real time was going to be as per schedule and not according to how the load is changing. And this brought about the idea of the automatic generation control, or AGC, or in those days it was called the load frequency control. And the tie line bias load frequency control was introduced in the 1930s. Okay, so think about it, that this was prior to anything people had not even thought of computers. So this was done by analog control, right? So you had, again, these measurements from the generators, from the tie lines, coming in, an analog controller, which is making sure that your generation, that your schedules, tie line schedules are met. In the 1950s, the idea of the economic dispatch came about, right? And this was, again, prior to digital computers. And the whole idea of the economic dispatch is to be able to dispatch generation according to the marginal cost of the generators to minimize the total production cost of generation. Okay? And this was also done by analog means. In fact, I look old, but I'm not that old to actually seen these analog computers. But I did see the original economic dispatch analog that was used by American Electric Power, and it's in their museum piece. And they're essentially they're wires. They're like they're called slide wires. They're like having multiple slide rules where you changed the cost curve of the generator in these wires, and then you moved a straight line across these wires to find out what the power should be for each generators. Okay, so this is all very interesting, but you can also see that the economic dispatch was the first thing that people realized that you could do with a digital computer when the digital computer first started, right? Because it was a very easy binary search that you could use in a very simple program, few lines, 10, 20 lines of program, and you can do an economic dispatch. All right, so, but of course in the 1960s, the digital computer came in, and we had what we call the SCADA AGC, the supervisory control data acquisition. So all of this hardwired data acquisition and supervisory control, which is the changing of the breakers, all got replaced by electrical signals, right? So you had signals coming in from measurement. So what you had to have is from each of the measurement points, you have to have a communication line. And so between the substations, you have some sort of communication. In those days, in the early days of the 60s, these were all microwave channels, very low bandwidth, 64 kilobytes, 128 kilobytes, some very small bandwidth. And similarly for sending out the signal for supervisory control, same thing. Okay, so that was the SCADA system. And then slowly, the economic dispatch was turned into the digital computer, which was easy. It was harder to turn the AGC, the load frequency control, into a digital algorithm. And the reason is, now people will think this is funny, but this is before Shannon's theorem. So there was a big debate in the early days of whether continuous control can be done by a digital computer which is non-continuous, right? So in fact, there are papers from the early 60s. There was a big debate between IBM and Leeds and Northrop. Leeds and Northrop was the inventor of the original AGC, and IBM was trying to bring in their computers into the control center, and they said, well, we can do AGC. So, and in fact, of course, you know who won. So we went to a fully digital control center by the end of the 60s. Most people have turned over into digital control centers, SCADA, AGC. Before I say this, I want you to think about the computers themselves. In the 60s, the only computers available were batch mainframe computers. And so they were not quite suitable for doing real-time things because they only did one job at a time. And there was no ability to interrupt things. So you couldn't do many tasks at the same time with the controller. And in fact, the computers that were used in the early days of the SCADA AGC were very special computers. They were actually special computers that were built for things like rocket control. Okay, so these were special computers. And then it was only in the 80s that these computers got changed over. We got the workstations, the basic, and then of course the desktop. And these are very interruptible computers doing multitasking, multiple things. So in the early days, so I started working on these kinds of things in the 70s. And the big issue at that time was there was lots of, all the SCADA AGC were already running. So then the question was, can you do more things online? And at that time already, companies like American Electric Power was trying to do the state estimator, except they didn't know that they were working on the state estimator. The name came afterwards. And they thought what they were working on was the real-time power flow, because the power flow had already been solved. The power flow equations had been solved in around 67, 68. So by the early 70s, AEP said, well, if you can remember what the power flow does is if you give it all the loads and all the generation, it tells you what the voltage is, right? So that's what the power flow equations tell you. And this is a nonlinear set of equations, and you know all the details. It's a difficult problem, but the digital computer was already being used to do this offline. So people in the control center said, well, we have all this instrumentation, we bring in all the generation, we bring in all the loads, we give it to the computer, and it should give us all the voltages. And it failed miserably. They tried this and it wouldn't solve. And the person who solved it was Fred Schweppe from MIT. And the reason he solved it was because, of course, he wasn't even a power engineer. He was a controls person, and he was at MIT. And AEP at that time had a program where they brought in professors for a summer to spend at the control center or in some capacity. And he was told that we're trying to solve this problem and it doesn't solve. But he was already working as a controls engineer on other kinds of control problems. And he said, well, this is a state estimation problem, all right? Because if you give the same number of data to a set of equations as the number of equations, then you can't solve it because there are noise in the data. So you never get the answer. But if you give it more data, if you over-define the problem, then you can solve it. And so he set it as a state estimation problem, and then he could solve it. And so that started this whole idea that you can now get a power flow solution in real time, which means now you can do other analysis on the real-time conditions of the power system, the typical one being contingency analysis. You can check how much overloading or voltage problems you may have because of your present conditions. If you lose a line, or the n-1 conditions was the main one that we worked on at that time. And this is when I started getting into starting my career on these kinds of problems. When I worked in those days, it was Control Data Corporation, and their EMS division got bought out by Siemens. So the company I worked with is still part of Siemens. And these are some of the things, as you know, were worked on for the first time. So by the end of the 70s, these were now commercially available for all control centers. So the control centers have, where by the end of the 70s we're doing these things. Now, what has happened now in terms of the applications haven't changed that much since the late 70s as to what we can do in the control center. What has changed is the architecture of the control center itself, because the computers have changed completely and the communications have changed completely in these 25, 30 years. And so what we are seeing now is that when we started doing this thing in the 70s, what we had was, like I said, so these special computers to do the SCADA, because these were special. But in those days, and then what we did was we put some mainframe computers behind these SCADA computers to use that data to solve the state estimator and then the contingency analysis. So these were high, what in those days was considered very difficult computational problems. All right. So, but you have to realize that in the 70s, even in the late 70s, a mainframe computer took up half of this room. And you have to have two of every computer in the, because of the reliability to back up. So you have to have two mainframe computers to run these EMSs, right? So, so in terms of, and even in the 70s, the communication channels being used were still relatively slow. So the data coming in was still about 4 seconds update of the real-time data. All right, 2 seconds, 4 seconds, maybe 10 seconds update of the real-time data. So these, over time, what happened is that in the 80s, the workstations came out. And the workstations can do both the SCADA function, because they had interruptible machines, and then it could also do the computation, because now these are much more powerful machines. So both the SCADA computers and the EMS computers, as we call them, the application computers, they were replaced by the same workstation. And suddenly you didn't have to have a duplicate of everything. You could, for example, have 3, 4, 5 workstations, and they could back up each other, because they were all similar kinds of machines. All right. So in terms of redundancy, and the cost of the workstations was much, much lower than the original mainframes. And as you probably know, if you think back on the computer industry, many of these computer manufacturers went out of business, who made mainframes, like the Control Data, the Sperry, Univac, all of these companies went out of business. IBM is the only one which survived, and it survived only because they were so big. Not because they made mainframes, because nobody bought their mainframes after that, right? So, so then, in terms of, some of you may remember, around the 90s, there was this big movement about open architectures. And the whole problem was that these control centers were only manufactured by about 3 manufacturers around internationally, European, American manufacturers. And that made it a problem of mixing and matching applications. So once your architecture of the control center is decided, say by Siemens, then the only applications that will run on them are the Siemens applications. And so the ABB applications will run on their control. So this became very difficult for people. It wasn't a very competitive market. Once you bought Siemens, you're stuck with Siemens and so on. So there was a movement about open architecture, which never actually happened. And part of that open architecture movement was this common information model. The idea was that if you can use the database common for all of the systems, and then you can exchange that. Even though the SIM model, some of you may be familiar with it, is accepted, and actually ENSO-E has been very very aggressive about pushing for the SIM model. The problem is that the vendors have been clever enough to somehow keep their proprietary software going. So now, just to give you an overview of how the controls are done, this is just a transmission system of the United States. I just put it up there because by looking at it, one glance you can tell where the people are on the map, right? So by the way, that reminds me, I'll tell you, I live right there. That's where I am, and in the Northwest, and that's the state of Washington, and that's why my university is called Washington State University, and this part over here is one interconnection. As you know, the North America has 4 interconnections, and in fact, if I do it this way, you can see this is the U.S. It only shows 3, but Canada is completely interconnected except for Quebec. Quebec is a separate interconnection, right? So we have Texas as a separate interconnection. We have Quebec up here as a separate interconnections. Other than that, there's only 2 big ones. This is rather large, about same size as UCTE, the Western European interconnection, right? So the purpose of showing all this is that I want to show you the number of control centers. Okay, so these little circles are what in America we call balancing authorities. So each circle is in charge of a particular area which balances load and generation, right? So the AGC is run in each of these circles, and there's roughly about 80 to 100 of these in the US. These little circles, and they used to be only an individual power company would actually control their load and generation, but many have now consolidated their balancing with neighboring companies. So for example, if you look at Texas, all the companies in Texas have agreed to jointly balance their load and generation. Okay, so some consolidation has taken place. Same thing for New York, for example, and others. But this one shows this next level up control center. Okay, so each color here has a control center which we call the reliability coordinator, and the reliability coordinator coordinates that area, the transmission system. Okay, so if you look at this, the Texas has its own reliability coordinator, so it's and that is separated from the others. It's not interconnected, and then the Western system has one reliability coordinator, which is separated from everything else. But you can see that the Eastern interconnection, which is all of this, is divided up into several different reliability coordinators. Okay, and then, but in general, these reliability coordinators is the upper level control center. So there's nobody above this level of control center, and then the balancing authorities are below this level. And this has become the standard architecture for controlling the grid all over the world. Okay, and you will recognize this one, right? And you can see the number of interconnections here are 3, and of course the white one here is the Russian interconnection, and the blue part is about the same size in megawatts, gigawatts wise as the Eastern interconnection in the U.S. And you're very well aware that each of these countries are like their own reliability coordinator, and then some of them below it will have other distribution companies that are underneath it, right? So, if you look at the map like this for China, for India, they all look the same. One level up for the transmission level coordination, and one level down for the generation load coordination. Okay, so now if I think of a control center, the control center, the way it used to work, well, it still does, is that we have these remote terminal units in each substation, and they have these communications to the first level control center, and then that's where your SCADA AGC is, and then above this would be the reliability coordinator. That I'll skip this. So let's talk about the future a little bit, or what is happening now and why all of these changes are coming into play. The big thing that is happening, the big change that is happening, is we are now able to measure more things, right? And because we have more communications, or cheaper communications than before, we can bring this data back to the control centers. Okay, so what do we mean by that? So if you, at the grid level, we're talking about phasor measurement units. So at the high voltage level, we're putting in a lot of phasor measurement units, which can measure both the magnitude and the angle. So in the old days, there was no measurement of the angles, which is a reference measurement, which has it only has meaning if you refer the angles to some base, right? So in the old days, we only measured magnitudes, voltages, currents, megawatts, megavars, whatever. But now, being able to do this because of the GPS connection, the other thing that has happened is you can measure. It has to be measured very rapidly, but not only that. In the old days, because of the microwave channels, which we started in the 60s, we only could get data at this very low baud rates. We could only measure every 2 seconds, every 4 seconds. And now we're talking about measuring every 30 times a second, 60 times a second at very fast rates. All right. The sampling, by the way, in the PMUs are done at much higher rates. Very high frequency sampling is done, but the data we are getting about 30 times a second or so. All right. So now the output rates are 30 to 120 times a second. So the data rates are much higher coming into the control center. Now, the big problem, of course, the control centers were never designed for these high data rates. Those control centers are still designed for the 4-second, 10-second rates of data coming in. And in fact, the funny thing is that many control centers are now tied to the substations with fiber optics. But they're still bringing in data at 4 seconds because that's what the SCADA software does. Okay, so this is a map of the US with all the PMUs mapped there. There's only about 1,400 of them. And I think in all of Europe, there's a similar number, it'll few less. Okay, the large numbers of PMUs are actually in China. They're in the thousands, many thousand. So then the question is, why don't we have more? Because these things are not very expensive. It actually costs a lot more to put them in, to install them, than to buy them. So, but the reason we don't have more, as I'll tell you in a bit, is we're not sure what we can do with them, right? So that's the big issue. But the other problem, of course, is that even the data is coming in at fast enough rates that you can actually do relay type applications, control type applications with this rate of data. Okay? And you see, because relays operate in a few cycles, right? So you're talking about milliseconds, tens of milliseconds or hundreds of milliseconds you can do control. Now you could never do that with the old SCADA AGC system because the data rates were much, much lower. Now with this you can, but one of the problems, of course, is that it depends on how you move this data, the PMU data. Right now the PMU data is being moved hierarchically from the substation to the control center, from the control center to the... So for example, if you have one of the examples may be that you want to know the phase angle difference between somewhere in Germany and Paris, right? Remember that something in Germany took out Paris a few years ago, right? I mean, Paris was blacked out because of a problem in Germany. So, so the angle difference there, but the only way you can look at the angle difference is if this PMU data was moved up to a point where these two angles can be compared, right? So what is happening is that we are using the same architecture as we did for our SCADA system for data movement, right? Hierarchically. So the only way you can see this, so there is nothing that immediately looks at 2 points in the West European, in the UCT system to compare. You have to go up the chain, and this, what that means is that this data, the PMU data, goes to some PDC, which goes to a super PDC, and so it's a hierarchical communication, which means that every point here is adding latency, adding more time delay. So you're not looking at it 30 times a second anymore by the time you get up there, right? So the thinking, of course, is that the communication system we've been using over the years for control centers is probably not the right communication system, this hierarchical communication system that we need now. We need more of a network communication system. Now, if you think of the telephone is a very, very network communication system. If you think of the cellular system, the mobile computers communication system, it's all. So the idea would be that each substation will have some sort of a server which is collecting all the data, all the PMU data, and then that server station just becomes a node in a networked communication system. So then you can get whichever data you need for a particular application. Okay, so the other part that is happening in terms of measurements is that at the distribution system now, you're getting much more measurements, right? And basically what is happening is your measuring systems, your sensors and your communications are getting so much cheaper that you can have more measurements on these systems. As you know, the smart meters are going in. I mean, most companies are now, most distribution companies are putting smart meters in their customers. On top of that, the distribution management systems are now becoming very common, which means that other than your customers, you've got medium level points, your nodes along the distribution feeder that are being measured. Okay. Now the smart meters are usually measured quite slowly, 5 minutes, maybe intervals, whereas your distribution feeders are being measured in the seconds, right? So you've got all these different levels of measurings going on the distribution system. Now, this is very lucky actually, because we have more other things going on in the distribution system that is coming quite fast, which is solar, wind, electric vehicles, building management systems, all of these things. So the fact that all of this is coming together is kind of good, but I don't think we have yet solved all the applications that are needed to manage all of these things. But this is going to be, in the old days, meaning 15 years ago, we only worried about this kind of thing for the transmission system because that was the only part which could actually justify the cost of all these measurements and communications and the control center computers and the operators and all of that. But now, all of this is becoming much more automatic, and so you're seeing a lot more activity on the distribution side than you're seeing on the transmission side. Okay, so this is a map of the distribution feeders in my town of Pullman, Washington, which is only 30,000 people, and there's only two companies there. One is the university, which is the large one, and the other one is Schweitzer Engineering Lab, which is the Schweitzer relays. They produce the Schweitzer relays in my town. So there's only 30,000 people there. There's only about 13 feeders and about 3 substations, 315 kV substations. All right, and this is what it looks like. My company, the power company there is called Avista, and this is what the distribution operator sees at their control center. We're here. The distribution company, of course, has a much bigger area. Pullman is one of their little towns, and these are the 3 substations, 115 kV, and those are the control things. And they have fully automated. They took Pullman as their first experiment to try smart meters in every home. All the university campus is run as a microgrid. So we have a lot of instrumentation and communication and so on this. This just happens to be the campus map. And this is what the distribution operator can see if you close in. So you have some possible switching for voltage control and so on, and for sectionalizing at this level. So the reason I put this up there is to show that this distribution management system is going to be much more active in terms of research. And we were in the lab downstairs looking at some of the things that Professor Gomez is doing here. Just because the management of the distribution system is going to get more and more complex as you put more and more things at this at that level. Okay, so there's a whole set of issues here about communications, about where the instrumentation should be. It turns out that the smart meters are not that useful in terms of real-time control because they're slow. On the other hand, much of the switches that are being put on the feeders are very useful because you can do lots of things with it. And so many of the applications are still being this. So few other things. Let's see, how much time do I have? I have plenty of time? No problem. All right. So a few other things. One of the problems in the power engineering business is that over time, different vendors have specialized in different things. And so people who were, the distribution management system and the energy management system are 2 things I've talked about. But there have been other things going on. Substation automation has been another big area where inside the substation, the control rooms have become completely digitized. People are using full fiber optics throughout the substations, and so on. Okay, the PMUs have to be integrated into the substation, and so on. So but here's a couple of other things that are the geographic information systems. The DMS actually is very dependent on the GIS. Okay, so these 2 technologies have come together now. But there are other things that also comes together with the GIS. Is one of one of the most useful things for using the geographic information systems is to send your crew for doing repairs. All right? You can follow the truck as it goes down, whether it's following the lines and doing that. So the outage management system, so as you get the telephone calls from areas that may be outaged, may have outages, and then you send the crew out, all of that requires a combination of what you can do with the DMS together with what you can do with the crew management and the outage management system. But you see, these started out as being completely different applications. All right, the outage management system only took the information from the phone calls and tried to detect which feeder was out. The crew management system was only sending out the trucks with the radio signals. And so these were all developed by different vendors. And we need to put all of these things together. And that's the whole issue today, is how to put together all of these applications. And the biggest problem is if you go to one company and you look at the GIS, it's one database. If you look at the outage management systems, it's another database. You look at the distribution management systems, it's another database. The databases, the displays are completely separate. And the big problem is that the vendors like it that way. And the power companies will have to force them to actually put them together, right? So that's the condition of the industry today, and I think it's not just up to the researchers who have been working on many of these issues for a long time, but it's a matter of the standard setting bodies, the NSOEs and the regulators within the countries to make this thing happen. Building automation, another thing that's coming in, and this is going to get more and more difficult, because in many cases, in the US particularly, the market system is now allowing large customers to play the market. Okay, what that means is you can not only buy, but you can also sell as a load, as a large industrial load. It's very common to play in the AGC market, in the load following market. Okay, you say, well, you want this much more generation, which is the same as reducing my load by this much. And you bid that into the system. And this is being allowed by PJM, which is one of the largest markets in the US, and many others. And so and this means that now the commercial buildings are trying to do the same thing. They say, well, we'll also bid into the market. Before, it was only the large industrial complexes, like petrochemical factories. But now the large buildings are trying to do this. And on top of this, you see some of the chains, Walmart. They're all putting in solar systems. And they want to bid into this market, because during the day they've got too much solar. They don't need all of it. So what are the kinds of things that we can do with all this new technology? All right, so at the transmission level, the big promise at the transmission level is wide area control and monitoring. Okay, monitoring, you understand, it's being done already, but wide area control means, if you think of the special protection schemes people are starting to use for voltages, and you see, you're going to see more and more of this because the PMUs enable you to do this. In real time, you're getting data 30 times a second. You can do special protection schemes. In fact, many of the relay manufacturers, like Schweitzer, they have whole divisions that take consulting from all the power companies to solve their control problems with their PMUs. See, for most relay manufacturers, there's no difference between their relays and their PMUs. It's the same thing, right? And so they will use the same boxes to solve your control problem. So for example, in the US, we have cases where if for a fault in the Southwest, the solution may be to open up some transmission lines in the Northwest, okay, 2,000 miles away. Okay, these are the kind of special protection schemes that people are using, especially if you have long distance lines. You know, they're in Russia, for example, they're using some of that. At the distribution level, you see, we talked about all the different things: integrated fault-forward control. You know all these words. At the customer level, you have the demand response, the optimizing the cost benefits. So all of these are opportunities for utilizing the new technologies. The question is which ones are going to come first, and how much are people going to do, and whether you can justify the cost benefits. You know, everything has cost and the benefits. But I also wanted to point out that some of these things will be easier to do if there is more standardization of communications, of these sensors, of the databases, and so on. I'm going to skip this. Some of the we are seeing usage of some of these more and more. For example, for PMUs, you know, many places are now the oscillation detection and the PMU only state estimator are being tried now. In some cases, you know, the vendors are actually selling commercial versions of these things. All right. Certainly, in the distribution, most of the DMSs claim they can do many of this. I think the problem they have is in trying to manage a lot of different things. For example, with electric vehicles as well as renewable energy and so on. Customers, I think I've talked about most of these things. I wanted to go back to this issue of standardization, because much of the standardization deals with databases being standard. You know, the way the vendor community has made this thing hard to do is by having their proprietary databases. So their software doesn't work except on their database. So whatever, and you already have too many databases in your company. Any power company has too many databases, and they should all be the same. And so standards are, so I can't emphasize this more. And then finally, everything depends on the politics, right? So if you think about what is happening today, much of the changes that are taking place is not being pushed by technology. Is being pushed by other institutional issues. For one big one everywhere is how to move to renewable energy. Okay, and in the U.S. now, there's a move. The only problem with this is it's not coordinated. Every state in the U.S. has a different target for renewable energy. All right, everybody has a thing which says by 2020 we will have 15% renewables. All right, but every state is different. Somebody has 2018, somebody has 2025. The percentage is different. California now even put out a target for storage devices. You have to have so many gigawatts of storage by such and such date. All right, so these are what is driving some of the use of these technologies. I think we are lucky that the technology is available to make some of these things happen, right? But it still is an issue. There are problems of coordinating in the case of in the United States, the coordinating between states is a huge issue. Here, of course, coordinating between countries is a big issue. And so we have different views on many of these things, and unfortunately the engineers are stuck in the middle, right? Because these things will be changed by the politicians, and they don't really ask the engineers whether it's feasible or not. But it's like Germany saying, well, we're going to shut down all our nuclear plants. Okay, so when I talk to the German engineers, they say there's no way we can keep the lights on if all the nuclear plants are shut down. Okay, and Poland is saying it's fine. We supply them with coal power. So I think I'll kind of stop there. All of this thing together makes up what we call the smart grid, right? Nobody has a definition of the smart grid, but if you think about it, it's all of these things together. The politics, the technology, the ability, the cost benefits ratios, all of those things kind of push us in this direction. And as I said before, the systems approach, I mean, the utilities will really have to push this, and it's not the vendors who will advance this fast. And that's why you turn to people like ENSO-E or NERC in the US to push these things. But they have their own constraints as to what they can do. But the technology is coming very fast, and in fact, it's the applications that are behind. And I think there is, in the last few years, there has been more interest in R&D in these areas than ever before. The last 30 years probably less so than today. So I think I'll stop there and take a few questions. Yeah.
Okay, thank you very much, Ajan. I forgot to say at the beginning that maybe some people will be following us remotely because we are broadcasting for our colleagues in other university which partners in the postgraduate program. So unfortunately this time is very early for folks from South America to follow because it's very early over there. So this time we'll not have any question from, for instance, Ecuador, which is typical. So let's begin with the question from the floor. Please, any question you may have? Microphone. Don't be shy.
I would like to ask you about the network of USA that is apparently independent, but there are some projects to merge all the interconnection networks in some kind of super grid, an overlay grid that integrate more renewables and can transfer more power at long distance. Can you tell me something about
Right.
that?
So there hasn't been any serious interest in merging the four interconnections. There's four interconnections: Texas, Quebec, and the Western and the Eastern. So, and these are already interconnected with DC lines. Okay, all of them. But there is no particular interest in synchronizing these. Okay, so on the other hand, there is the issue of if the renewables, more and more renewables come in, then the more solar is concentrated on the southwest. Okay, Southern California, Arizona, that area, and the wind is mainly concentrated in the middle south to north, the middle band, going from Dakota, South Dakota, North Dakota, Nebraska, and down into the Texas area. Okay, so, and if you think about it, there's nobody lives there. It's basically farmland in the middle, and it is along pretty much the border of the Western and Eastern interconnections. Okay, so if we're going to move a lot of wind power from that area, then we need transmission lines to the west and transmission lines to the east. Okay, so there have been proposals for building transmission lines in either direction, and but as you know, building transmission lines is a difficult thing. There's too much opposition to building transmission lines, and so it's coming very slowly. On top of that, the politics gets in the way. All right, so if you live in, let's say, Minnesota, and somebody from North Dakota wants to build a big transmission line all the way across your state to Chicago, then the state says, I have no interest in this HVDC line that'll go across me, and I just look at it. I don't have any advantage for it. So there is all these kinds of problems that are coming on. So, and this is what I meant by institutional issues. There is, in the case of the US, there is no national plan, because these are all state has regulations over the transmission, over the distribution, and so on. Same thing in Europe also. You have very similar issues over here. So I don't know if that answered your question. Yeah.
There is no more question. I can exchange some idea with you. Is as you have perfectly explained, we are facing a boom of information at all levels. At the transmission system, basically because of PMUs or IEDs, yeah. And at the distribution system because of smart meters, distribution automation, new sources of data. So this will be leading to 2 or 3 orders of magnitude higher amount of data to be sent and processed, both. So we have 2 bottlenecks here. One is the bandwidth of the communication channel, which might be solved, but also the capability to digest, to process all this huge amount of information in the real, as needed.
Right.
So it's not. I don't see clearly where this is going to. In the future, how do you think will we be moving to solve this bottleneck to peer-to-peer architecture, to fully distributed, or still hierarchical, delegating some computing power to the lower level, like the substation or even the secondary substation or something like this? So where are we going to in this sense? Because otherwise we will not be able to, as you properly say, to handle and to properly use and take advantage of this investment on new channel, on new sensor, and new. So where are we going to?
So my view of this thing is that we have 2 kinds of issues here, and in terms of the control of the grid. Okay, we have always had this dichotomy, because if you think of the way things are done today, there's the people at the control centers. Okay, their job is to look and not to do too much, but just to make sure that things are being done right. So, but these are human operators, and so their reaction time is much larger. So, but they're the ones that can think what can go wrong, what may be right, what needs to be changed. So this is a different time frame. And then we've always had the protection and control systems, which operates automatically without thinking on event or on some thing that happens, so it reacts. Okay, so these 2 things are coming together right now, because more and more data can be brought into the control center, so the operator can look at it. Most of the time, they can't absorb this level of information. So the main question at the control center is, what are you going to do with what information do you need from this data that is going to be useful to the operator? Okay, one set of issues. So this is a good place for R&D, all right, and not just technical R&D. This has got operations, it's got training of operators and so on. The other side, which is where the distributed stuff comes in, is that relays and controllers have traditionally been local, right? So the substation says my voltage is low, I change this, all right? Or I got a short circuit over here, I open this breaker, right there, okay? No intelligence being spread out. This is all local. So what the PMUs allows us to do is now saying, I have an event over here, but I will make the change over there. Okay. Now this kind of thing, you don't want it to be you don't want the communication structure for this to be hierarchical. You want this to be distributed, a peer-to-peer type of communications, so that it can occur instantaneously. Okay, and this gives us a lot more ability to do things. Okay, so on the one hand, the automatic controls become more powerful only if we can solve some of these distributed control problems. On the other hand, the human operator problem gets better if you can give them the right information. Okay, over the last 10 minutes, the angle separation between this point and this point has become so much more. Okay, and so here's an alarm, or here's an alert, or you know, the n minus. We just lost this generator, and within a few seconds, we know what my n minus 1 conditions are going to be. Okay, and you alert the operator on that basis.
In my opinion, the border between these two different phases, I mean, the fully automatic and the operator-assisted, slower, is being getting more diffuse because, right. You know, for instance, PMUs can be used on both sides. Can be used for automatic, you know, yeah. Protection. And actually, Red Eléctrica is installing PMUs just for protection, basically.
Yeah.
So, but they can also be used as the state estimator, EMS, and this for slow operator information. So. The border is getting more diffuse.
Yeah.
So
technically, there is no border.
Yeah.
Right. There is no border between these issues. But the applications is where you have to be clever. You have to decide what is going to be the application. Is it going to be an automatic application, or is it going to be information for the operator, or maybe both?
Yeah.
Okay. And I think this is where we are lagging behind in trying to design the applications that's going to be the most useful. Okay, like you said, many people are already using the PMUs for controls, for special protection schemes, and starting to use some controls, some run-back schemes for generation or something like that, right?
Yeah.
So, yeah.
And there is another level, I think a third level, the back stage, which is related to commercial activities. For instance, smart meters are providing every hour in Spain, and in the past every month, but now hopefully every hour, so information of energy consumption. So this is useful for backups to get paid the energy every month or whatever. But smart meters, they are remotely connected with the DMS.
Right.
So they can be also used for network operation. I mean, the other, you know. So there is another border with the other backup. So in the past there were 3 levels: the backup, the backstage, the EMS, and the protection. And now the borders are getting diffused. And this gives me to my later question, which is related with the business models. I mean, it's not only we have many more data, we have many more agents. We have storage, electric vehicle. We have active consumer who have photovoltaic on the roof, and self-producers. So the business models are changing. So and there are new opportunities for R&D, not only but also for making money. For instance, this aggregator role, which is something like a local market, could be somewhat subordinated to the wholesale market, something like this. So what do you think also with this prospect in the future of the DMS and this?
The business model is probably the most confused at the moment in terms of, because there are several different things operating at the same time. One is the clean energy issue, which is more or less being driven by politics. Right? All of us want clean energy. The question is, how much are we willing to pay for it, and how fast? Right? So, that's a political issue. That
the technology is over there. The problem is who pays.
Right. But the business model has evolved over time. How a power company makes money or stays in business has evolved over time. So one big issue, for example, is the net metering. And I don't know if you have that here, where essentially if you have photovoltaics in your roof, you feed the power back and the meter runs back. Is that what you have here?
Well, I will explain during the lunch. It's a controversial issue.
Okay.
Very
so
controversial.
We'll stay out of it.
But during the lunch, I will tell you the details.
Okay. So in the U.S., in most states, the state government, or the Public Utility Commission, as we call them, have mandated this net metering. Okay, so you have... So one of our alumni who lives in California has the biggest house in the San Francisco area, and he has big estate, and he had what at one time used to be in the estate the stables, the horse thing, which has been turned into a garage. So he put photovoltaics all over the roof, and he never pays an electric bill anymore, right? Now this is the richest person in that area who's not paying for any of the distribution lines or transmission lines or anything, right? Yeah. And he's very aware of it, of course. He did it with calculations. But poorer people who don't even have roofs, they live in apartments, they're paying for the infrastructure for the thing. So this is a very, very controversial issue, right? Yeah.
Not only that, because if there are more and more people are defection from the grid, those remaining will have to pay more. And probably poorer people will have to pay more because richer will get away from the grid.
So then the question is how do you make this fair? How do you make this equitable for everybody? Well, the business model originally was not fair, because whether you live in the city near a substation or if you live 20 miles on a long feeder, you pay the same price. No, that was the business model. So the decision on what is fair is done, as a society, not by. And as things change, you're going to face this, and people will have to decide. The big problem is that this decision making was also split up into many levels. Some are decided by the state, some are decided by the country, some are decided, and this is very, very difficult. And then once you start looking at transmission lines, once you are in the rural area, the distribution lines used to be overhead. Now, of course, even in the rural areas, they want the distribution lines to be underground. Somebody has to pay for all these things that we want to be good, right? So the business model is the first thing that's going to be. But, we live in countries, I think, where these decisions have been made over time with compromises, and I think that's the way we'll go.
Over 100 years history.
The only thing I find funny is that the politicians and the people who are running businesses, even the people at the top of they think that the engineers are going to solve it all. They make the decisions, the engineers are going to solve the problem.
And the other good thing is that this is good for us power engineers. So this gives us more work and more chances for making money. So this is good for students. There are many students here, so I encourage them to follow the track of power engineering. Any other question from the floor?
My question is I'll try again. My question was about what you said about.
Try it again.
Where is it?
Try it.
Okay. When you spoke about the balancing and the reliability authorities, and you put the example in the US, for example, I saw that PGM system had a reliability authority. But the translation of this into the European case, I got a little lost in that case, since the UCT, in fact, is a power frequency regulation, perhaps establish the rules for interchanges, but the real authorities are national authorities in charge of both things, I think. Perhaps I didn't see the translation from the American case to the European case. What are the balancing?
Well, there are a lot of variances between Europe and the only thing that is the same is that the electrical structure is the same, right? There's transmission, there's generation, there's transmission, there's distribution and loads, right? But other than that, all of the rules are quite different. For example, in most European countries, the owner, the high-level transmission is owned by one entity, like Red Electrica, and they are also the controls. They are in charge of the reliability of that transmission system. In the U.S., even PJM is a non-profit entity, and their only job is to operate the grid of the PJM, the high voltage grid, and also run the markets. But they do not own the grid. The grid is owned by individual transmission owners, many of them. Okay, so again, there is a big issue about, the PJM will say, well, it would be nice to have more PMUs, all right? Then they have to convince all the transmission owners that because the transmission owners have to put in the money for the PMUs, all right? Which is different from, say, RTE. They say, I need more PMUs, so you go to the high voltage substations and you put. So there are all these kinds of differences on top of, but the biggest difference is that in the US, these large entities were formed because of market reasons. The PJM was formed to run the PJM market, the day-ahead auction market. That was their main reason to form. This is true for New York ISO, New England ISO, all of these. But there are whole areas of the US where there are no auction markets, all right? And they operate more like the European system where they have bilateral transactions. They will say, we want to import over a long period of time some generation from Poland, for example. Okay, so that's a long-term market, but not the auction market for the bidding market for next day. So there are all these little differences, and it'll probably, nobody actually understands all the differences, but that gives you some flavor of the differences, yes.
Okay, I think it's no more questions, so thank you very much.